a space recording hidden by NASA for 40 years, the third sound that could shake your entire worldview. Today, we're going to dive deeper into some of the most terrifying sounds ever recorded in space, from the eerie screech of a comet passing by to the deafening roar of supermassive black holes, and even the echoes from a black hole collision that occurred 5 billion years ago. You've probably heard that sound can't travel through the vacuum of space. While that's true in the conventional sense, since sound waves require a medium to propagate, it doesn't mean the universe is silent. On the contrary, it's filled with mysterious vibrations waiting to be decoded. Using a technique called sonification, scientists can transform data from plasma waves, X-rays, and even gravitational waves into sounds that human ears can perceive. In a moment, you'll hear 4 of the most frightening sounds from outer space. We'll explore how scientists captured these strange noises and the profound meanings behind each one. We all know the phrase, "In space, no one can hear you scream." And it's true, because sound waves need matter to travel. But other types of waves, such as radio waves, plasma oscillations, X-rays, and gravitational waves, can be converted through sonification into audible signals. What's fascinating is that the resulting sounds are not only otherworldly, but they also carry unique and valuable information about celestial bodies and cosmic phenomena, like solar winds, pulsars, or black hole mergers. In my previous video, episode 104, I introduced some space sounds mainly focused on the sun and the planets within our solar system. But today I'll be sharing newer discoveries from far more distant and lesser-known regions of space. These include, for example, sounds recorded by the first probe to successfully land on a distant moon, or from a supermassive black hole nestled deep within a remote galaxy cluster. But before we embark on this strange sonic journey, let's ease into it with something closer to home. A familiar landmark within our solar system, Saturn. Saturn's rings are made up of countless fragments of rock and ice. Most of these particles become ionized under solar radiation, turning into charged particles. Furthermore, Saturn's magnetic field is filled with these energetic particles, which move freely, interact, and create complex, unpredictable phenomena, accompanied by eerie and chilling sounds you're about to hear. The dust particles and charged particles in Saturn's rings are far from stationary. Simply put, when these charged particles collide and interact with the plasma in Saturn's magnetosphere, they are subjected to a force known as the Lorentz force. This force causes them to spiral along magnetic field lines, generating oscillations in the plasma, known as plasma waves. In 1997, NASA launched the Cassini spacecraft into orbit around Saturn. As space dust struck the spacecraft's body and instruments, it created tiny plasma clouds. These clouds were converted into audio signals, allowing scientists to hear the electromagnetic interactions occurring in space. The resulting sounds were truly bizarre, giving listeners the eerie sensation that these were sounds humans were never meant to hear. Try listening and feel it for yourself. But that's not the end of the story. In its final, glorious journey in 2017, Cassini recorded a hauntingly strange audio clip, the sound of plasma waves traveling from Saturn to its moon Enceladus, also known as Mimas. What made this recording even more unsettling was the fact that it was one of the last pieces of data Cassini ever transmitted back to Earth. Just 2 weeks later, the spacecraft, after 20 years of dedicated service to humanity, was intentionally plunged into Saturn's atmosphere to avoid contaminating any potentially life-bearing moons. Imagine this: if you were Cassini, that would be the last sound you'd ever hear. However, Cassini wasn't the only spacecraft to transmit audio data derived from celestial vibrations. In 2014, the European Space Agency, ESA, launched the Rosetta mission into space. During its exploration of Comet 67P, Rosetta sent back some truly mysterious data that you shouldn't miss. And that brings us to the second stop on today's cosmic audio journey: Comet 67P Churyumov-Gerasimenko, the primary target of the Rosetta mission. To date, it remains the first and only comet on which a man-made device has successfully landed. Comet 67P orbits the Sun along the outer edge of the solar system, with a period of about 6.5 years. It's believed to contain primordial material over 4 billion years old, dating back to the birth of the solar system. In addition to studying the comet's composition, Rosetta also aimed to understand how solar wind affects its coma and tail. To accomplish this, Rosetta was equipped with specialized plasma measurement instruments. Rosetta was equipped with a suite of sophisticated instruments, including a Langmuir probe designed to measure electron density and oscillations in the plasma environment surrounding the comet, as well as a magnetometer used to detect variations in the magnetic field caused by plasma waves. Combined, these instruments provided scientists with a comprehensive view of the plasma dynamics around the comet. However, detecting magnetic waves from a comet isn't entirely new. Similar plasma wave patterns had previously been recorded from other comets, including the famous Halley's Comet. What made Comet 67P unique wasn't the fact that it emitted plasma waves, but the sound it produced. The song of Comet 67P, as scientists have called it, stands apart from any sound ever recorded from other comets. This suggests that Comet 67P possesses unique physical properties never before observed in similar celestial bodies. Now, you're about to hear that very recording. Interestingly, the audio can be broken down into distinct sonic components. The rhythmic tapping, like the beat of a drum, represents periodic fluctuations in plasma density and the impact of solar wind on the comet's magnetic field. Meanwhile, the constant humming in the background reflects the continuous oscillations occurring within the plasma environment. Have you ever imagined what a black hole might sound like? Then brace yourself, because from Comet 67P, we now travel 240 million light-years away to the Perseus galaxy cluster. At the heart of this cluster lies one of the most massive supermassive black holes ever discovered, with an estimated mass of 17 billion times that of the Sun. Such colossal black holes typically emit intense X-rays and ultraviolet radiation, which originate from their accretion disks, superheated layers of gas orbiting the black hole at millions of degrees Kelvin. To study these X-ray sources, NASA launched the Chandra X-ray Observatory, positioned in high Earth orbit. Its mission: to search for X-ray data that could help unravel the true nature of black holes. Chandra is equipped with an ultra-sensitive electronic detector capable of capturing incoming X-ray photons and converting them into digital signals. This capability allows scientists to paint vivid pictures of black holes, the remnants of supernova explosions, and many other catastrophic cosmic phenomena. In addition to observing black holes, the Chandra X-ray Observatory also enables scientists to study the distribution of hot gas in galaxy clusters. In 2003, it collected some exceptionally intriguing data. Thanks to its high-resolution imaging and advanced spectral analysis capabilities, Chandra allowed researchers to examine the X-rays emitted from the hot gas surrounding black holes, particularly within the Perseus cluster, home to one of the largest supermassive black holes ever discovered. By 2022, scientists revisited this X-ray data and for the first time converted the wave frequencies into sound. To their astonishment, they discovered the lowest frequency sound ever detected in the universe, a note 57 octaves below middle B, B4 on a piano. At such an extraordinarily low frequency, a single cycle of the sound wave from this black hole would take about 10 million years to complete. To put this into perspective, humans cannot hear any sound with a cycle longer than 50 milliseconds. So NASA scientists used data sonification techniques to compress and raise the frequencies into a range audible to the human ear. The result? A bone-chilling, spine-tingling audio clip, often described as the kind of sound that makes you feel an urgent need to use the restroom. Listening to it might send a cold sweat trickling down your neck. If you're holding your phone right now, watch out for your pants. And if you manage to hear it without flinching, congratulations, you have nerves of steel. But then, a serious question arises. Why do scientists study these sounds? What value do they offer to astrophysics? The most fascinating insight is that these sounds may help us understand the evolution of galaxy clusters. A galaxy cluster can contain hundreds or even thousands of galaxies. The space between them isn't empty. It's filled with a thin, hot plasma known as the intracluster medium, ICM. This medium is denser, hotter, and about 6 times thicker than the gas found outside galaxy clusters. One hypothesis suggests that sound waves emitted by black holes can transfer energy into the ICM, helping to heat and maintain its temperature. And since we know that star formation is influenced by the temperature of the surrounding environment, this implies something extraordinary. The sound waves from black holes, even though we cannot hear them, may play a critical role in shaping the long-term evolution of entire galaxy clusters. Our final destination is a historic triumph, one that even Einstein once doubted humanity would ever achieve. If he could somehow sense this discovery from the beyond, he might very well rise from his grave tonight, overwhelmed with emotion. Back in 1916, Einstein predicted that black holes could generate gravitational waves. To visualize this, imagine tossing a stone into a calm lake. The ripples that spread across the water resemble gravitational waves. Except these don't ripple water, but rather the very fabric of space-time itself. As these waves travel, they stretch and compress space ever so slightly. The effect is so tiny that even Einstein believed we would never be able to detect them. And yet, just over a century later, humanity has built a global network of gravitational wave observatories and successfully detected these waves from nearly 100 different cosmic events. Facilities such as LIGO in the United States, Virgo in Europe, and CAGRA in Japan have worked closely together not only to confirm the presence of gravitational waves, but also to pinpoint their origin and direction in the vastness of space. What's astonishing is how these detectors work. Unlike traditional telescopes that use lenses or mirrors, these observatories rely on lasers. Scientists direct laser beams down 2 long perpendicular tunnels, each several kilometers in length. When a gravitational wave passes through Earth, it subtly alters the structure of space-time, causing tiny changes in the length of the tunnels, changes as small as 1/10,000th the diameter of a proton, or about 10^-1 meters. These minuscule shifts affect the frequency of the laser beams, much like tightening or loosening the string of a guitar changes its pitch. When converted into sound, this data produces the characteristic chirp associated with black hole collisions. Each collision has its own acoustic signature. When 2 small black holes merge, the resulting sound is long, deep, and gradual. In contrast, the merger of 2 massive black holes produces a sharp, powerful, and brief sound, like the thunderclap of the universe. One of the most remarkable recordings is that of 2 black holes colliding 5 billion years ago, merging into a larger black hole and releasing energy equivalent to 5 solar masses, all in the form of gravitational waves. This remains the most distant and powerful gravitational wave event ever recorded by humanity, a majestic moment in the history of the cosmos. Clearly, calling the universe silent is a gross oversimplification. In reality, the universe does speak, but only to those who know where and how to listen. And now, thanks to science and technology, we are finally beginning to hear its voice.